Hi, people. We're going to talk about an element of circuitry that explains a good bit about batteries, um, and it has to do with this idea called internal resistance. Okay, we've been assuming so far that you hook let's say, a 9-volt battery into a circuit, and that it automatically always provides that potential difference, but it doesn't, right? And here's what I mean. Well, if you just have a battery and you hook a voltmeter up to it, regardless of the condition of the battery, like a D battery or a C battery or a AA or a AAA, they're all 1.5 volt batteries. And if you hook, I could take any battery out of our bin of old batteries and you hook a voltmeter up to it just by itself, and it'll say 1.5 volts. Pretty darn close. But you put that battery in a circuit and make it actually do something, and you measure the voltage across the battery, you're going to get something different. All right? And it's because of this idea called, or this real functional occurrence called internal resistance. All right? So what really, there's a couple ways to see these in questions, but in a lot of cases schematically you'll see this. You'll see like a little resistor right after a battery, and let's say that's an actual, what we call a load resistor, and a lot of times they'll do this. All right, that dotted line will try to indicate that this little R resistor in there is an internal resistance. Now, we're not saying that inside batteries the manufacturer places a little resistor. All right, what we are saying is that that just due to the way batteries work, there's a certain amount of electrolyte and a certain amount of there's the stuff in the battery, and well, you run out of the ability to perform the chemical reactions necessary to provide potential difference. All right, and so it acts like there's resistance in the battery that can change over time. All right, a couple of things we talk about also. The battery itself has what's called an EMF. All right, this means EMF, or electromotive force. All right, it's a voltage. It's a potential difference. We measure it in volts. I don't want to put that. I'll do that still in square brackets for units. All right, R is what we call internal resistance. Measured in ohms. All right, this R here, which could be, it doesn't have to be one resistor, it could be any number of resistors that are actual resistors. That's what we call the load resistance. Also measured in ohms, right? And there'll be some current that runs through this circuit. Now, we also call this, if we look at the potential difference from there to there, we call that the terminal potential difference. So if I write this, if we actually connect a voltmeter across here, when this thing is measuring, when it's running current, we call that, lots of times people write it like this, VPD. It's called the terminal, terminal potential difference. And of course, it's measured in volts. Okay, terminal meaning the ends of the actual battery. All right, now I think I'm going to overlap here. Oh, no, yeah. So what that says is that over time, let's say there's a certain amount of current that we can put, that we could read if we were to put an ammeter there. Ammeter measuring current. Okay? Well, over time, what happens is this internal resistance in there gets bigger. All right? And that resistance means that there's actually some loss in potential, almost say sort of quote across that resistor, even though it's not an actual resistor. Right? So if that resistance goes up, basically the resistance of the whole circuit goes up. And then the amount of current in this circuit will drop, and then the potential difference across this load resistor can drop. All right? So if you think of a battery, a light bulb in a battery, a light bulb in a flashlight, over time, the internal resistance of the batteries increases, and that makes the current that actually goes through the light bulb get smaller, and that makes the brightness of the light bulb not as bright. Okay? Let's see here. So a couple of equations we can write. First of all, we can say that VPD, the potential difference that you actually measure across a battery that is supplying a circuit with current, is the EMF minus whatever drop in potential there is across the internal resistance of the battery itself. Okay? Now, if we were to rewrite this, or we could almost actually redraw this circuit in a couple of ways. One is it behaves just like this circuit. Move this guy. Come here, fella. Come on, you. It behaves just like this circuit with an equivalent resistance of R plus R and a potential difference of E. Okay? It also behaves just like this circuit with just a plain old load resistance R and a potential difference across that battery that we just call VPD. All right? Notice, here I take the resistance out of that battery. Here I leave that resistance in the battery, so the potential difference across it is not the full EMF. Okay? So we could write things like, I mean, that's one thing we can definitely say. We could say 2E equals I R plus R. Okay, that's just using Ohm's law with this circuit. And 3, I'd say from this circuit, we can always just say that the terminal potential difference provides the current across that load resistor. Okay? So sometimes these things are a little bit tricky to figure out which one of these you need to use, but that's, you know, that's the, those are the 3. Okay? But, you know, if you want, just so we're sure, like you can use the internal resistance as an actual, I mean, it is a resistance. And if it's, you know, in our big circuit number 1 here, we really are saying that that internal resistance is in series with our load resistor R. So therefore, this is just finding us really REQ, right? Right here, REQ, the R plus R. And of course, a different circuit that didn't just have one resistor, one load resistor R, we'd still follow our same rules as ever to find our total equivalent resistance. Phone's ringing. All right, it's going to take a little bit of jockeying for a minute. I got to move a question, but let's just do that now. So here are a good couple questions we can address. The first one, a battery has that internal resistance and that EMF. What's the maximum current that can be drawn from the battery without the terminal voltage dropping below 8.9 volts? So that one's pretty straightforward. We're going to say that the terminal potential difference is the EMF minus any loss in potential across internal resistance. So what's the maximum current? So we're going to say I equals E minus V over little r. Okay? So let's see. E is 9 minus the terminal potential difference. So that's 0.10 volts divided by 0.012 ohms. Yes? Okay. Significantly more challenging here. A generator has this terminal voltage when it delivers 10 amps and 106 volts when it delivers 30 amps, right? So that makes sense based on what we said. The more current you try to drop, well, here it is. Sorry, the more current you try to run, the bigger this whole thing gets and the smaller the potential difference that you can actually provide to some other load resistances. Okay, but no matter what, at least for a certain amount of, I mean, for a generator, not even a battery, right? This is always the same thing, or it's going to be the same thing in this case. A generator doesn't run out of stuff to provide a chemical reaction, but based on, it's really like its functional parts, they provide some sort of internal resistance, and that's always the same thing. Just like the EMF that it can produce is always the same thing. The two things that it can change, the two things that are really related, are the amount of current it provides and therefore the potential difference across its terminals. All right, so here's what I would say. There's basically a V for 110. I'll call this an I at no, wait, sorry. This goes for, it can do 110 volts when it delivers 10 amps. And it can deliver 106 volts when it delivers 30 amps. But notice, the E and the R are the same. So therefore, I can solve this, well, solve both of these for E, or solve both of them for I. I'll solve both of them for E, and then we'll have a way to get R out of there, okay? So I'm going to say that E is V110 plus I10R. So that's E from this one. E from this one says it's V106 plus I30R. So I'll get all the R stuff over here, move the V's around here. V110 minus V106 equals I30R minus I10R. So this is actually just 104 volts. What happened there? It's not 104 volts, it's actually 4 volts. 4 volts, and let's see, this is, well, 30 amps times R minus 10 amps times R, so that's 20 amps times R. Therefore, R is 0.25 ohms. Okay? And then, R just goes in there and we solve for E. Okay? So if I use the first one, I get E. Why? Yeah, sure. E is, what do we say? For example, 110 plus 10 amps times 0.25 ohms. So that's 112.5. And if I were to put it into here, right, that's 106 plus 30 times 0.25, and that gets you the same thing. Is it? Yeah, it would help if I did my short division a little better, wouldn't it? Or short multiplication? I don't know. Is that even a word? So, 4 divided by 20 is actually 0.20. So then we're plus 10 amps times 0.2 ohms, and that's 112. And then if we do, okay, 106 plus 30 times 0.2, yeah, that's another 6, so there's your 112 again. Okay, so there's your EMF, 112 volts. Okay? But the nice thing to notice here is that, and even for a battery, at any, in any short amount of time, R doesn't have much time to change. Okay? I use this generator here, so we're just saying no matter what, its internal resistance and the EMF it is capable of are always the same. Okay? All right, folks. See you soon. Good.